Let's explore how to find the nth derivative of the function y equals x to the mth power, and understand the patterns that emerge based on the relationship between m and n. Let's start by taking the first few derivatives to see if we can spot a pattern. The first derivative is mx to the power of m minus 1. The second derivative is m times m minus 1 times x to the power of m minus 2. And the third derivative is m times m minus 1 times m minus 2 times x to the power of m minus 3. Let's analyze the pattern we're seeing. For each derivative, the power of x decreases by 1, and we multiply by one more term from m, decreasing by 1 each time. Following this pattern to the nth derivative, we get m times m minus 1 times m minus 2, and so on, until m minus n plus 1, all multiplied by x to the power of m minus n. This can be written more elegantly using factorial notation. The coefficient becomes m factorial divided by the quantity m minus n factorial, times x to the power of m minus n. Now, let's consider three different cases based on the relationship between m and n. Case 1. When m is greater than n, we use our factorial formula. Case 2. When m equals n, all the x terms cancel out and we're left with just m factorial. Case 3. When m is less than n, we eventually reach 0 because we're trying to differentiate more times than we have powers of x. Let's put all of this together in one comprehensive formula. The nth derivative of x to the m equals m factorial when m equals n, 0 when m is less than n, and m factorial over m minus n factorial times x to the m minus n when m is greater than n. Let's look at a quick example. Let's say we have y equals x to the fourth power, and we want to find the second derivative. Here, m equals 4 and n equals 2. Since m is greater than n, we use the third case of our formula. Plugging in the values, we get 4 factorial over 4 minus 2 factorial times x to the 4 minus 2 power, which simplifies to 12x squared.